Have you ever looked closely, really closely, at a £1 note? The intricate design engraved and printed in a variety of coloured inks is really impossible to copy. But just in case the design isn't enough to deter forgers, there are other complications. When you hold a note up to the light, you can see the watermark, another face of Sir Isaac Newton. And running inside, right through the middle of the paper, is a metal strip. You can see it here in an old, torn note. And what about the paper? Well, it's tough and strong, but it was designed before inflation. When prices went up, we began to use more £1 notes more often, and nowadays a £1 note circulates for only about 9 months. It gets more handling than it was designed for. That's one reason why we have coins. On average, metal coins circulate for about 40 years. But inflation has brought problems here as well. People now find themselves carrying a lot of loose change, and that means more weight in your purse or pocket, and a lot longer wait in the queue for tickets. And although machines like this seem like a good idea, they can't handle worn notes. So what can be done? To help solve the problems, the 20p and the £1 coins were introduced. But what sort of metal should a new coin be made of? Well, coins are made from alloys, which are a mixture of metals. So-called copper coins are a mixture of copper, zinc and tin. Copper on its own is too soft and would wear away quickly. So-called silver coins are a mixture of copper and nickel. Nickel is an expensive metal, so just enough is added to the copper to give the alloy its colour. The pound coin is made from another alloy, nickel brass. This is the recipe for a mix, known as a charge, that will be fed into the furnace that makes the nickel brass. First, the copper. The skip is loaded with 313 kilograms of copper and then weighed. The weighing machine is adjusted to ignore the weight of the skip. Next, add 27 kilograms of nickel. This takes the weight in the skip up to 340 kilograms. $112 kilograms of zinc, and the total moves on to 452 kilograms. Finally, a copper-manganese mix. Just 6 kilograms of this to complete the charge for the furnace. A total of 458 kilograms of metals, which makes up the recipe for the alloy nickel brass. First, the mixture of metals is melted in an electric furnace at a temperature of over 1000 degrees Celsius. But how do they know that the 458 kilograms mixture is right for the coins? Well, when the mixture is molten, a sample is taken to be checked. The molten metal quickly cools and hardens. But it's still very hot. After quenching, It's cool enough to be handled and sent on to the laboratory for analysis. Before it can be analyzed, the surface of the alloy sample has to be machined to give it a smooth, flat, clean surface. The machined sample is analyzed in an X-ray spectrometer. This determines the precise metal composition of the alloy. We can't tell you the exact composition. It's a closely kept secret to prevent forgeries. But so long as the analysis shows the mixture is correct, the signal is given to go ahead. The molten charge is tipped into a second furnace which holds up to 1,500 kilograms. This store of molten metal means that the next process, casting, can be continuous. The molten metal is cast from the furnace through 2 water-cooled graphite dies, where the metal cools and hardens. It comes out as a continuous, stiff, rigid slab, about 200 millimeters wide and 13 millimeters thick, from which 10-meter lengths are cut. After casting, the surface of the slab has to be removed. This is done in a scalping machine. Inside the machine is a cutting tool like this. These hard metal blades scalp the slab, producing a swarf waste which is recycled. Coming out of the scalping machine, the thickness of the slab has been reduced by about 1/2 millimeter, from 13.32 to 12.79 millimeters. But it's not thin enough. In this rolling mill, under enormous pressure, the slab is reduced in thickness first to 7 millimeters, then to just 4 millimeters. And at 4 millimeters, the metal is no longer stiff and rigid. It's flexible enough to be coiled. At the next stage, 5 coils are joined together. They're joined by welding. Welding is a process by which the 2 ends to be joined are melted by an electric arc in an inert gas atmosphere to prevent oxidation. The molten metal flows together, and when it cools, it produces a very strong join that looks like this. The 5 coils, when they're joined together, weigh about a ton, and this continuous strip has to be rolled once more. Under a force of 100 tons, the strip is reduced from 4 millimeters to 2.83 millimeters in 3 passes through the rollers. Before it goes through the rolling mill, you can see that the strip at 4 millimeters is much thicker than the 1-pound coin. But strangely enough, when it comes out, it's thinner than the coin. We'll see why later. This is a blanking press. The rolled strip is fed into the machine, and inside, hard tungsten carbide cutters cut out the blanks that will become the coins. The perforated strip is recycled and returned to the furnace. The machine rejects any damaged blanks, and they are recycled. This damaged blank, for instance, was cut out of the welded part of the strip. Sometimes an occasional damaged blank does get through, which is why these special sampling tubes are used, and why these blanks, and later on samples of the finished coins, are checked by eye. The next stage for the blanks is a trip through the annealing oven. Inside the oven, the blanks are heated to a temperature of 700 degrees Celsius, then slowly cooled. Annealing means to soften, but the softening process produces a dull, stained surface on the blanks, which is removed in the pickling process. In the pickling process, the blanks are washed in sulfuric acid and tartaric acid. After rinsing, the blanks are dried in a hot air cabinet. Here, you can see the difference between a stained blank on the right after annealing and a shiny, lustrous blank after pickling. This is the rimming machine. The blanks are rolled and squeezed through a channel like this, which not only impresses the letters on the edge of the blank, it also raises the rim. A blank, before it has been squeezed through the channel, is not a tight fit. But afterwards, the blank is thicker at the rim than in the middle, which explains why the finished coin is thicker than the rolled sheet we saw earlier. Raising the rim protects the surface of the blank, and later the surface of the coin. The blanks are now ready to be pressed between dies that will turn them into coins. The process of making a die begins with a plaster model, designed and carved by an artist. It's on a much bigger scale than the coin. A rubber mold is made from the plaster model, which reverses the image. The rubber mold is mounted on a board, and copper wire electrodes are attached, 2 at the top and 2 at the bottom. The mold is then completely and carefully covered with a layer of graphite. The mold is sprayed with a conducting solution, a mixture of silver nitrate and formaldehyde. In this way, a surface that conducts electricity is prepared for the next stage, which is electrolysis. The mold now becomes the negative electrode in the electrolytic process that in 2 hours deposits a layer of pure nickel over the mold, 0.05 millimeters thick. This thickness of nickel provides a hard surface, but it wouldn't be stiff enough on its own. So into another electrolyte, again as the negative electrode, but this time for 3 days. The result, 2.5 millimeters of copper on the back of the nickel, which gives it the rigidity it needs. The excess copper is trimmed off, and the rubber mold removed, leaving a perfect copy in nickel. This electrotype copy, as it's called, is now mounted in wax on a reducing machine, which will copy the design down to the size of a coin. At one end of this arm, the fine details of the design are picked up by this pointed tracer, which is carefully centered. At the other end of the bar is the cutter. This is also carefully centered onto a soft steel block. The tracer moves from the center to the edge, at the same time as the design slowly turns. The effect of this is a spiral cut, with all the details of the design being reduced by the bar and transferred by the rotating cutter to the soft steel block. Oil on the block helps to lubricate and cool. The first cut takes 12 to 14 hours. The final cut 20 to 24 hours. But with special film, you can see it all happen in less than 30 seconds. In the soft steel block are all the details of the original design. But before it can be used as a punch, the soft steel has to be hardened by heating to 850 degrees Celsius for 50 minutes, cooling quickly to room temperature, then leaving in a salt bath at 180 degrees Celsius for an hour. And this is the hardened steel reduction punch. It doesn't have all the details yet that appear on a coin, and is just the first stage in making the dies that will press the coins. The reduction punch is mounted in a hydraulic press. Underneath, and carefully centered, is placed a soft steel block. A force of 100 tons is used to press the punch into the soft steel. This copy is called a matrix, and it's at this stage that any details are added to the design. Here, the beading which appears inside the rim of the coin is being hand-punched into the soft steel. It's a highly skilled job. Next, each impression, and there are 100 of them, and the whole design is carefully checked. Then the soft steel matrix is hardened and becomes the master die. Working punches like this are made from the master die, and these in turn are used to make as many working dies as are needed. These are the coin presses. Blanks are fed into the presses and directed into slots which carry them between the two dies. Above is the die we have just seen being made, and below is the die with the queen's head. When the blank moves into position, it's squeezed between the two dies by a force of 50 to 60 tons. At the same time as the impression of both dies is being made on the blank, the metal is being forced outwards to form the rim with its milled edge. The raised rim is important because it keeps the faces of the coins apart and so helps to protect them from wear. As we saw with the blanks, the coins are also sampled and carefully checked before being automatically counted into bags of 500. The bags are sealed, checked by weighing, and then stacked and stored, ready for delivery to the banks.